Welcome everybody to this afternoon session of this Mini Moon online seminar series, number 11, which is the third talk today. We have two talks already in the morning, and that's the first talk in the afternoon. And this talk will be given by Professor Yoshifumi Saito of ISET's JETSA. Before he gives his talk, I want to say a few words to introduce him. Professor Yoshifumi Saito, he got his PhD from University of Tokyo, and his professor was Atsuhiro Nishida. Am I right? Yeah, Professor Nishida, and I met him. I knew him almost 20 years ago. Almost 20 years ago, and when he was still very young scientist. Already then he was very busy, very busy, building instrument and working on the Kaguya plasma instrument. And as you can see, hear from him later on, he's a super instrument, scientist, and not just building instrument, but also on the plasma physics side. Now he's very heavily involved. He's very heavily involved in the BB Colombo mission on the Japanese spacecraft, which will go into Mercury orbit in 2025, right? 2025, on its way already, and then and he has this he's a very intricate, very advanced plasma instrument measuring iron and electrons, but he will tell you, what he will be measuring, able to measure at Mercury, but tell us about his results on the moon by Kaguya. Yeah, Saito-san, please.
Okay, thank you very much, Wing-san, and thank you very much for the very impressive short movie and music. Okay, today I will talk about the interaction between Solarwind and lunar magnetic anomalies revealed by Kaguya map-based observations. And my first slide shows the magnetic anomalies map made by electron reflectometer on Kaguya. And as far as I know, this is the most precise electron reflectometer magnetic anomaly map on the moon. And the intensity of the magnetic field is shown in the right-hand side. The strongest magnetic field is a few hundred nanotesla. So the magnetic field on the moon is not so strong, rather weak. But there are so many magnetic anomalies on the moon. And talking about Kaguya, it was previously called Serenological and Engineering Explorer. And after the launch, it was named Kaguya. And it was launched by H2A launch vehicle on September 14th, 2007. So it is more than 10 years before. And it impacted on the moon on 10th June 2009. And 14 mission instruments were on board, including our instrument. And our instrument is for surface environment measurements. And magnetometer and plasma analyzer is our instrument. And today I will talk mostly about these instruments from my instruments, particle instruments. But on Kaguya spacecraft, there are several instruments for science at the moon and science from the moon, including particle instrument and magnetometer and plasma wave instrument, and also plasma imager to image Earth's magnetosphere. And also, there is a daughter satellite to perform the radio science, radio occultation measurements. And today I will mainly talk about the data obtained by PACE and LMAG, that is the plasma instrument and magnetometers, especially making emphasis on the plasma data. And this figure shows the Kaguya map-based instrument. And we have two electron spectrometers, ESS1 and ESS2, and two ion spectrometers, IMS and EIES. And one of the ion spectrometers, IMA, is this is the mass spectrometer. The mass resolution is as high as 15. And the purpose of this map-based instruments were to understand Solarwind-Moon interaction and to understand the ions originating from lunar atmosphere and lunar surface, and to detect the magnetic anomalies using electron reflectometer, and to understand the lunar wake structures. And this is the picture of Kaguya spacecraft, and our instrument, electron sensor ESS-1, is on the spacecraft panel facing the moon, and another electron analyzer, ESS-2, is on the opposite side. And mass spectrometer is on the surface facing the moon, and another ion sensor for ion energy spectrum observation is on the opposite side. And this figure shows the magnetometer. It is on the 12-meter mast in order to avoid the interference of the current generated by the spacecraft in the spacecraft. And so magnetometer sensor is here. And it is a 3-axial flux gate magnetometer. And the minimum range is plus/minus 64 nanotesla, and sampling rate is 32 Hertz. This figure shows the field of view of the phase sensors. The mass spectrometer IMA and ESS-1 is always facing the moon, and ESA S2 and another ion sensor IEA is always looking against the moon surface. So these IEA and ESS-2 mostly measure the solar wind, and ESS-1 and IMA mostly measures ions and electrons from the moon. But when the spacecraft go into the wake region, the IMA and ESS-1 measured solar wind for some time. And after exiting, just before exiting the wake region, the IMA and ESS-1 again observed the solar wind. And MapPace observed 3D low-energy electron distributions and 3D mass-identified low-energy ion distribution at 100 kilometer altitude for about 1 year between 14 December and 26 December 2008. And at 15 kilometer altitude, it made observation for about 2 months between 26 February 2009 and 16 April 2009. And after that, the periapsis becomes much more lower than that, as low as lower than 30 kilometer altitude. And it made observation between April 16th and June 10th, and impacted the moon on 10 June 2009. So the moon is the celestial body nearest to the Earth without global intrinsic magnetic field and thick atmosphere. So solar wind directly interacts with the lunar surface, and we want to know what this interaction is. And this slide shows the summary of what we discovered around the moon using ion mass spectrometer observations. And this bottom panel shows DET spectrograms. The horizontal axis is the time. From here to here is 2 hours. That is Kaguya's 1 revolution around the moon. And the vertical axis is the energy. From here to here is 10 eV to 10 or 20 keV. And this panel shows the schematic sphere showing showing the different population of the ions, and the shape is the same, of course. And the orange part shows the solar wind ions, that is just entering into the wake region and just exiting from the wake regions. And when the Kaguya spacecraft is on the day side, the number 1 population, this is the solar wind protons backscattered at the lunar surface, are observed. And above the magnetic anomalies, we observed these red populations, solar wind protons reflected by magnetic anomalies. And we also measured much higher energy ions, that is self-pickup accelerated or reflected or backscattered solar wind protons. This is that's number 4. And another component is here shown by thick blue, and these are the ions originating from the lunar surface or lunar atmosphere. So these are mostly heavy ions. Okay, and this data was obtained by making first low energy ion mass spectrometer measurements at 100 kilometer altitude around the moon. And looking at each component, each populations, number one, scattered and solar wind protons is generated by solar wind direct impact on the moon surface. And number two, magnetically reflected solar wind protons are generated by reflected ions by the magnetic anomalies on the moon. And the solar wind incident ions and reflected ions generate these low frequency waves. And some of the reflected ions are accelerated picked up by the solar wind electric field up to 9 times the energy of the solar wind and go into the wake regions. And at the boundary of the wake, when the ion intrudes into the wake, the low frequency wave excitation at the wake boundary was observed. And also, when the moon entered into the wake regions, along the magnetic field, electrons are absorbed here, and waves are again excited. So this is the global lunar plasma environment, and this is a result from comprehensive measurements of magnetic field, plasma waves, and plasma particles on Kaguya. But today I will concentrate on these scattered and reflected solar wind protons. This figure shows the solar wind and the moon surface. And when the solar wind collides with the moon surface, if the solar wind directly collides with the moon surface, the solar wind ions are backscattered at the lunar surface. And because this is the interaction between the solar wind and the solid materials, solar wind ion loses energy. This figure shows the spectrograms of the ions going into the moon. So this is the solar wind. And the second panel shows the ions from the moon. And this is from the mass spectrometer. And the third panel shows the solar zenith angle. And the bottom panel shows the longitude and latitude of the Kaguya spacecraft in the ME coordinate system. And again, from here to here is 2 hours. So it is 1 revolution of Kaguya spacecraft around the moon. And this blue bar indicates that when the spacecraft was on the day side. And we can see that these are solar wind ions because IEA is always facing against the moon, and this is on the day side. And these 2 components observed by IMA are also solar wind ions, because I explained before, when the spacecraft go into the wake region, just after a short time went into the wake region, it observed solar wind. And also just before short time exiting the wake region, it also is again measured solar wind. So these are solar wind ions. And this component shown here by the white circle is the scattered solar wind ions at the lunar surface. And the energy of this component is lower than the original solar wind because it is interaction between solar wind and solid materials. On the other hand, when there exist magnetic anomalies on the lunar surface, the solar wind ions are reflected by magnetic anomalies on the lunar surface. And if solar wind ions are simply reflected by magnetic field, so the solar wind ions do not lose energy. And concerning the interaction between the solar wind and lunar magnetic anomalies, we can find many simulations in research. And the first one may be this by Erika Harnett-san. And this shows the Pini magnetosphere on the moon generated by the interaction between the solar wind and lunar magnetic anomalies. And after that, there are many simulations. And in 2020s, 2012s, we can find these simulation results by hybrid code simulations. And in 2015, the first 3D particle in cell simulations were reported by Jan Beck-san. And also some whole MHD simulation was reported by Z-san. And at the same time, these particle simulations showing the more small-scale structure is also reported. And new simulation by these people was also reported in 2020. But today I will concentrate on the observational results, what was observed on the moon, lunar anomalies. And this figure shows the data obtained at 100 kilometer altitude. And the top two panels show the electrons going into the moon and electrons from the moon. And the third panel is the ions going into the moon, and the fourth panel is the ions from the moon. And this panel shows the magnetic field intensity by black line, and blue line shows the altitude of the spacecraft. And the bottom panel shows the longitude and latitude in ME and SSE coordinate system of the Kaguya spacecraft. And again, this is a 2-hour plot, and it is one revolution of Kaguya spacecraft around the moon. And when the IEA measures these intense ions, these are on the day side, and these are the Solarwind ions. The lower energy ions are protons, and higher energy ions are alpha particles. And we can see that there is a strong magnetic field was detected here at about 820. The longitude is minus 160 or 70, and latitude is minus 50 or around 50. So this is magnetic anomalies in South Polar Aitken regions. And looking at the ion data from the moon, we can see these intense ions from the moon, and the energy of these intense ions are nearly the same as solar wind energy, but a little bit summarized and a little bit decelerated. At the same time, we can see that electron data, we see that electrons are slightly heated. And talking about the solar wind ions entering into this magnetic anomalies, solar wind ions are slightly affected, a little bit, energy is a little bit decelerated by magnetic anomalies. So this is the characteristic signature over magnetic anomalies observed at 100 kilometer altitude. And this data shows, this data was obtained at 15 kilometer altitude. And again, we can see some magnetic anomalies around here, and this is all again above the over the South Polar Aitken regions. And different from the previous data, we can see that there is no scattered solar wind protons when the magnetically reflected ions are observed, indicated by these white arrows. And this can be explained like this. If there is a magnetic anomaly here, and that is enough strong, the solar wind cannot fully enter into the magnetic anomaly regions. So it doesn't collide, it cannot collide with the moon surface. But outside this magnetic anomaly, the solar wind can directly collide with the moon surface, impact the moon surface. So impacted solar wind are scattered back inside the scattering cone. The size of the scattering cone is about plus minus 40 degrees. So in that case, when the spacecraft crossed the magnetic anomalies in low altitude, it cannot measure the scattered solar wind as shown in this figure. However, at the high altitude, because it is inside the scattering cone, it can measure the scattered ions even when the magnetic reflected ions are observed. So this can explain this ET spectrograms observed like this. Okay. And this figure shows the data obtained at 25 kilometer altitude. The format is the same as before. So this is again one revolution of Kaguya around the moon. And we can see that this characteristic signature observed at low altitude, well, we can see that there is a strong magnetic anomaly here. This is again, the longitude is minus 178 and latitude is minus 30 and 30. So this is again over magnetic anomaly in south polar Aitken regions. And we can see that reflected ions are observed here. And the highest energy is nearly the same as the solar wind. And we can also can see that acceleration of the electrons like this. This is just look like an inverted V, usually often observed in the auroral region in the Earth's ionosphere. And we can also see the deceleration of solar wind ions like this. And the deceleration can be observed both protons and alpha particles. And the decelerated ions are slightly heated. And looking again at these reflected heavy ions, these ions are, and heavy ions, including alpha particles, are also decelerated. And looking at the reflected ions by magnetic anomalies, a significant amount of reflected ions are observed, and they are further heated and decelerated. Okay, so this is the signature observed at 25 kilometer altitude. And zooming into the electron accelerated regions and ion decelerated regions over strong magnetic anomalies, we can see that the electrons has the pitch angle nearly parallel to the magnetic field, and these are precipitating electrons. And comparing the electron energy spectra and ion energy spectra indicated by this blue color and red color, we had this figure. And the blue color indicates the ions and electrons outside the magnetic anomalies. And red line indicates the electron and ion energy spectra obtained inside over the magnetic anomalies. And looking at the electrons, the inside over the magnetic anomalies, the electrons are accelerated, comparing these blue and red lines. And by moving the blue lines about 150 eV per charge, these two lines nearly overlaps. And looking at the ion energy spectra, we can see two peaks indicating protons and alpha particle peaks. And blue color is again, that is outside the magnetic anomalies. And red color is the energy spectra over magnetic anomalies. And when shifting the blue lines about minus 150 electron volt eV per charge, these two lines overlaps. So this indicates that this means that electrons are accelerated by 150 eV per charge, and ions are decelerated about 150 electron volt charge. So the same energy over the magnetic anomalies. Okay, so we have several data and investigated the relation between the electron acceleration and ion deceleration over magnetic anomalies at 25 kilometers altitude. We have this plot, and this line indicates that the deceleration and acceleration of electrons and deceleration of ions and acceleration of electrons has the same energy. Okay, and in order to explain what generates this electric field, we consider the size of the lunar magnetic anomalies. The size of the lunar magnetic anomaly in this case was about 100 kilometers, and it is calculated from the orbital speed of the Kaguya spacecraft, that is 1.6 kilometers per second, multiplied by detected period, that is about 1 minute. So this is about 100 kilometers. And in this case, the ion density is 4, So the ion inertial length is 115 kilometers. So the size of the lunar magnetic anomaly and the ion inertial length is nearly the same. Such cases, we can apply the whole MHD equations, and the whole term is shown by this. And this indicates that the electric field is proportional to the magnetic field as twice the magnetic field, double the magnetic field over density and length of the electric field. So we compared these parameters, electric field times the length of the electric field regions. So it means the electron energy and the right-hand side parameters. So the result is shown here. The horizontal axis is the electron acceleration energy, and the vertical axis is these parameters. And we can see these two parameters have some correlations like this. So it means that electric field over the magnetic anomaly is generated by the decoupling of the motions of the ions and electrons on ion inertial length scales. Okay, and we can see in more detail of the velocity moment of electrons and ions around magnetic anomalies. And top panel shows the density of electrons and ions, and the green color shows the electron density, and red color indicates the ions from the moon, ion density from the moon, observed by mass spectrometer. And a blue color indicates the ion density going into the moon. So this is almost the Solarwind ion density. And the density of ions and electrons corresponds with each other. And looking at the ions reflected back from the moon's surface, we can see that in the largest case, in the highest case, 50% of the density of the ions are reflected back. And looking at other parameters, this is the density of reflected ions and Solarwind ions. The density of the reflected ions shows that reflected ions are reflected to much larger area than magnetic anomaly size. So this indicates this red line shows the magnetic field. So the strong magnetic anomaly is observed between these vertical black lines, but we can see that reflected ions distributed a much wider area than this magnetic anomaly regions. And we can also see that this large black dot indicates the temperature of the reflected ions, and comparing with the Solarwind ion temperature that is indicated by this blue dots and blue line, the reflected ion has much higher temperature than the incident Solarwind ions. And this blue line shows the reflected ion velocity, and this red line shows the Solarwind ion velocity. So this indicates that reflected ions lose Solarwind energy. Okay, and because the IMA is mass spectrometer, we can also see the mass species of the ions from the moon. And the right-hand side figure shows the Solarwind ions, and Solarwind includes mostly the protons, and the second largest component is the alpha particles shown here. And talking about the scattered protons, we can see protons, but almost no alpha particles were observed. And talking about the reflected ions by magnetic anomalies, we can see protons here, but we can also see a small amount of alpha particles like this. Okay, so we're taking into account all the observed data. I made this schematic figure, and this shows the interaction between the Solarwind and lunar magnetic anomalies. And Kaguya spacecraft observed crossed the magnetic anomalies at 25 kilometer altitude. And Kaguya observed upward electric field, and this accelerates the incident electrons, and this decelerates the incident ions. And looking at the reflected ions, we can see that those ions lose energy, and also they are significantly heated. So that means that there exists some ion heating region below the spacecraft of altitude 25 kilometer altitude. Okay. And the size of the magnetic anomaly in this case was about the ion inertial length. So hollow MHD can explain by using the hollow MHD, this electric field was generated by the motion difference of the electron as ion motion. Okay, so the next question is, what is the plasma structure below 25 kilometer altitude? And this table shows the altitude of Kaguya during map-based operation. And these three lines I already explained using the previous figure. And just before impacting the moon, the Kaguya as altitude was shown here. On 2nd June 2009, the Kaguya's altitude was 70 kilometers and between 70 kilometers and 30 kilometers. And on 5th June, the highest altitude was 80 kilometers, but the lowest altitude was below 10 kilometers, that was 9 kilometer altitude. And just before impacting the moon, 9th June 2009, the Kaguya's altitude was 84 kilometers and 7 kilometers. And on June 10th, the Kaguya impacted the moon. So this red line indicates the period when the Kaguya spacecraft altitude was below 10 kilometers. And this is an example of the ET spectrograms observed at below 10 kilometer altitude around magnetic anomalies. And the format of this figure is the same as before. And you can see that, and this blue line indicates the Kaguya's altitude. And you can see that the lowest altitude is nearly 0. In this case, 7.4 kilometer. And we can see a very strong magnetic field when the Kaguya spacecraft altitude was very low. And when this data was obtained, Kaguya spacecraft was in the magnetosheath regions. And we can see electrons and signatures and ion signatures above these magnetic anomalies. Okay. And this is the enlarged version of the ET spectrograms. And this data was obtained at 7.4 kilometer altitude. And these two panels show the electrons going into the moon and coming from the moon, and ions going into the moon and ions coming from the moon. And we can see strong magnetic anomalies here because the altitude of the spacecraft is very low. And the position of the spacecraft is shown in these three panels. And here to here is the 15 minutes. So this is a quarter of the one revolution of the moon. And we can see that these signatures accelerated electrons like this. And it is a little bit difficult to see, but these electrons also accelerated. And we can see ions. This is the ions going into the moon. And the energy of the ions are slightly decelerated when the electrons are clearly accelerated. And also we can see the ions from the moon side, like this, over a strong magnetic field. So this is nearly the same as the signature we observed at 25 kilometer altitude. So accelerated electrons and decelerated and reflected ions. And so decelerated ions and reflected ions are observed where magnetic field is strong. But the difference is that, well, we observed a set of accelerated electrons like this. One side is very faint, but anyway, we observed a pair of accelerated electrons. And we can also see that high energy part of electrons are lost like this. And looking at the pitch angle of electrons, we have this figure. And these are the ET spectrograms. And the top panel shows the magnetometer measured magnetic field. And the second panel is the modeled magnetic field. And we can see that the pitch angle distribution of these accelerated electrons are well distributed to 180 degrees, but are slightly strong at the precipitating part. And the second accelerated electrons also shows nearly the same signature. But between them, the electron pitch angle distribution is nearly concentrated in the 90 degrees, around 90 degrees. And next, we will see the pitch angle distribution of ions of the same data. And zooming into these regions, the top panel shows the IEA spectrograms. So the ions are a little bit decelerated like this. And the pitch angle of ions going into the moon is shown here. And the left-hand side and right-hand side ions are sheath ions going into the moon. And when the over the strong magnetic anomaly, the distribution or the temperature of the ions seems to rise or becomes high. And this panel shows the ions from the moon, and the pitch angle distribution of the ions is rather wide comparing the sheath ions. So pitch angle distribution of the decelerated ions and are wider than magnetosheath ions. And in order to check if the ions enter into the moon is heated or not, we made this plot. And this green line indicates the ions going into the moon. And over the strong magnetic field, the ions energy is becomes lower. So ion energies are decelerated, ions are decelerated. And this red line indicates the temperature of the ions, these ions going into the moon. And looking at comparing the temperature in the left-hand side and right-hand side, and the temperature over strong magnetic anomalies, we can see that temperature rises up here like this. So so it means that the incident ion's temperature becomes high, and the energy is decelerated over a strong magnetic anomaly, even at 7.4 kilometer altitude. And this is a little bit different from the 25 kilometer altitude, where the Solarwind ion temperature incident, Solarwind incident into the magnetic anomaly, its temperature is not so much heated like this, but the reflected ions are heated very much. Okay. So the observational summary is shown here. At an altitude of over 25 kilometers, Kaguya observed electron acceleration and ion deceleration by electric field above Kaguya. And Kaguya observed magnetic field and plasma below 10 kilometer altitude around magnetic anomalies. And below 10 kilometer altitude, trapped electrons on the closed magnetic field line were observed in the central region where high energy electrons were lost. And it was surrounded by the regions where one side of the magnetic field was connected to the moon and accelerated electrons were observed. And it is consistent with the plasma structure around magnetic anomalies obtained over about 25 kilometer altitude. And even at an altitude lower than 10 kilometer, decelerated ions were observed. And different from higher than 25 kilometer altitude, the temperature of the decelerated ions were higher than that of the ions before deceleration. So I made this figure, and at 25 kilometer altitude, when Kaguya crossed magnetic anomalies, it observed accelerated electrons and decelerated ions. And at 25 kilometer altitude, the reflected ions shows the energy decrease and also significant heatings. And when the Kaguya crossed the magnetic anomaly at lower altitude, lower than 10 kilometer, it observed electrons, accelerated electrons, paired accelerated electrons. And also it observed decelerated ions, and the ions temperature was heated. So there exists some ion heating regions between 10 kilometer altitude and 25 kilometer altitude. And the electrons, accelerated electrons, are flow like this and impacts the moon surface. So the accelerated electrons preferably impact the moon's surface surrounding the magnetic anomalies. And the surface of the moon will be charged up by these electrons, I guess. And this should be observed in the future on the moon. So, okay. So these are the results. Accelerated electrons will impact the moon surface in the region surrounding the magnetic anomalies. And ion heating region exists between below 10 kilometer and 25 kilometer altitude. Okay. So what are the possible targets of the next plasma exploration around the moon? I myself want to understand the plasma structure above magnetic anomalies and also the lunar surface charging. So in order to do so, lunar surface plasma measurements at the foot of the magnetic field around magnetic anomalies will be very interesting. So we need plasma instruments on moon rovers. And I want also understand the mechanism of ion heating in the region between lower than 10 kilometer and 25 kilometer altitude. There exists some ion heating regions there. So we need plasma instruments on moon landers or reusable sounding rockets from the moon. And also we need micro or nano satellites released from Lunar Gateway. So this figure shows the future observation of the lunar magnetic anomalies. The small micro nano satellites released from the Lunar Gateway is very useful, and that will cross the ion acceleration region. And also the plasma instrument of moon rovers will be able to detect these accelerated electrons impacting the moon surface. And also, if we can realize these reusable sounding rockets from the moon surface, it can directly measure these ion heating regions in the future. Okay, so this is my last slide. Well, the plasma measurement in spacecraft starts from the Earth's ionosphere and magnetosphere, and as the place we can go is expands, and the place where we can make plasma measurement expands also. And there are many planets in our solar systems, including Mars and Venus and Jupiter. And these planets are categorized into two kind of planets, with non-magnetized planets and planets with strong magnetic field. And another category is the planet with air and without airs. And Moon and Mercury are the typical celestial bodies without airs. And Moon is the airless bodies and without global magnetic field. And Mercury is the airless bodies with global magnetic field. So, and we are going to visit both celestial bodies. So we can say that Japanese planetary plasma exploration is in the mid-term of the 20-year quest for the plasma environment around airless bodies. So we visited Moon by Kaguya spacecraft between 2007 and 2009. And we are going to visit Mercury. And Bepi Colombo MEO spacecraft is now on its way to Mercury. And it was launched in 2018. And it will arrive at Mercury in December 2025. So in the future, we can compare the plasma data between Moon and Mercury. And I hope that we can understand the interaction between the solar wind and these airless bodies in more detail in the future. Thank you very much.
Have you finished, Saito-san?
Yes.
Okay.
Really?
I thought I lost my connection. Okay, that was very, very interesting talk, I think. learn a lot from you. Now, let me first ask the audience. Anyone has questions to ask Professor Saito? I think this is a very comprehensive talk. I think he puts many talks, at meetings together into one more comprehensive, coherent talk. Before we got 1 or 2 slides. Or anyone, please raise the hands and ask questions and unmute yourself. If not, I have a couple questions to ask Saito-san. One thing is that you talk about magnetic anomalies, but are you referring to any particular magnetic anomaly region, like Lunar Gamma, or any one of them?
Yes, I myself is investigating any. Well, my interest is in any magnetic anomalies. But I think Nishino-san has ever investigated the magnetic anomalies and the over Grisham borders, well, the Lunar Gamma, is that right? So, and he has discovered many new things. And but I think the well, most of the magnetic anomaly has the common signatures, and I think that is very important. So I'm investigating all kinds of magnetic anomalies, actually.
Yeah, because I was just told that the NASA has selected a rover mission, a land mission, to Lunar Gamma. So the second thing is that in your summary slide, I mean, actually the one slide number 46. Here you have the magnetic field, the IMF, more or less pointing towards the moon. Yeah. But how about if it's perpendicular?
Well, that is, I'm not sure.
I mean, it never happened?
Well, no. Well, as far as I see, the signature is near, well, the similar signature can be observed. So I have not yet investigated in detail about the magnetic field directions. So that should be made in the future. I'm very interested in that. There should exist some difference, but as far as looking at the overall signatures, the signature is nearly the same.
And also, you at the end you said you see trapped electrons, right? Yeah. And what that means that even for thermal electrons, it will trap and hence producing a kind of formation of a mini ionosphere.
Yeah. Okay. You mean that the trapped electrons around here?
Right. I mean, like photoelectrons, and then they're forming a higher density ionosphere region.
High density, or not so high, because comparing with the outside, the density is low because this is cavity, something like a cavity.
They from the radio occultation measurement, people said that they measured that there was a lunar ionosphere with a density something like a 50 per cc.
Yeah, right. Well, as far as I see, observed at the 7.5 kilometers, the density was not so high. So they may observing the much lower altitude. I'm not sure what they're observing that.
And I see a Nishino-san on the screen. I was thinking that just the Solarwind interaction with the magnetic anomalies were a very good topic, special topic, for discussion. Nishino-san, you want to say something? Please go ahead.
Yes. Are you talking about Ishi Beijing International Team?
Right. I mean, there will be plenty of things to talk about.
Actually, we had such kind of meeting several years ago in Ishi Beijing with Jan Decker, led by Jan Decker.
Well, if you're interested, think about that. Yeah, I mean, there may be a more simulation and more data analysis and so on. Are you planning, Saito-san, are you planning a NATO satellite mission to the moon now?
Well, Well, in Japan, we have several moon missions. One is a SLIM, that is the moon lander, but no plasma instrument on board. And I'm now participating in the LUPEX mission, that is the Lunar Polar Lander mission. And I'm now developing the mass spectrometer for neutral particles, and that will be on board the moon rover in the future.
Yeah, that would be very interesting also. But that's going to the South Pole, right?
Yeah, right.
Yeah. Not going to where you want to go. But what I'm saying is that in case you are interested, you have the interest in planning or starting a NATO satellite mission to study the magnetic anomalies, like you're saying, please tell us. We'll be happy to participate.
Okay, thank you.
In participate in the study, in the feasibility study as a way to learn about the moon. Yeah.
Oh, okay. Thank you.
Any other one has any question? Anyone in the audience wants to ask a side question? I mean, that this is a very comprehensive and clear presentation, and telling almost everything about about the magnetic anomalies interaction with the Solarwind electron and ions. I'm not sure that in near future there will be other measurements as a detail as presented here, because it just so happened that they have this kind of can look at the moon and the Solarwind at the same time, so they could measure this. If no further questions, and then I would end this session, end this talk for now, and want to thank Professor Saito again for giving this talk. That I know that he's so busy, but he's used to be busy, so I think that and we will continue the discussion in future. Thank you again. Yes.
Thank you very much for providing me with this very good opportunities. I enjoyed very much. Thank you.
Yeah, with great pleasure, and thank you a lot. Thanks a lot.